Hello, welcome back. This is lesson 11 of my playlist Waves and Wave Phenomena. This part is on the HL unit, topic 9. We will be discussing diffraction gratings and multiple slits. In your textbook, you can find these graphs given for a single slit diffraction pattern and a double slit interference pattern. We have seen these two before. We have also discussed that this intensity pattern applies to an ideal case where the two sources are assumed to be point sources with no width at all. And in that lesson, you might remember that I hinted at we will get back to this, and that is what we see on this graph. Now, you see that the similarity between the single slit diffraction pattern and the graph that you see here. This is actually a combination of the first two. This is what you would see with two source interference with diffraction effects. This is what we call Young's double slit experiment. Without ignoring the width of the two sources, we will actually see in reality, which we have an example over here, that the interference pattern in terms of intensity as you move away from the center line will stay in the envelope. We will still see the maxima at these locations, but the intensity will decrease as you look away from the center angle, and it will stay inside this envelope, which is what we see here. So let's explain what happens as we increase the number of slits. We have the envelope for a single slit. As I increase the number of sources here, please watch what happens to the width and location of each maximum. Okay, now I'm going to demonstrate what causes what we saw. So each of these little red pieces of paper is going to represent a single slit. So as you can see, a single slit, and that is the width of its central max, right opposite. I'm now going to add another one. So I'm not changing any of the properties of my single slit. I'm not making it wider or smaller. I'm not changing the distance to the screen. I'm not changing wavelength, nothing. All I did was add an identical one. And obviously that identical one had its own central maxima, just like the first one did. Let's increase that to 3, to 4, to 5. What we should be seeing is the maximum that we observe on the screen will be within the range that they all overlap. So as I have two sources, for example, this would be the limits of the central maximum. At 3, we should see more intensity, but a narrower range for the central maximum. As we increase the number of slits without changing the separation and the width of each slit, the effect on the pattern happens to be the maximum centered in the same locations. However, they become narrower and more intense. Here's another view of what we just explained. That would be the single slit diffraction envelope, the diagram for two sources, 3 and 5. That blue line is the single slit envelope, the pattern with two slits, with 3, with 4, with 5, and with 10. The image becomes brighter and more distinct as we increase the number of slits. The next discussion will be on the diffraction grating. A diffraction grating is dividing a single slit into smaller pieces. So instead of adding identical slits, I am now going to split the single slit into smaller sections. Let's watch. That's the central line. Bright fringes as seen with 80 lines per millimeter, angle to the first maximum. With 100 lines per millimeter, angle to the first maximum. With a diffraction grating of 300 lines per millimeter, angle to the first maximum. With 600 lines per millimeter, we didn't see any. Why not? Let's try to explain with this simulation. This is the image of what we see on our screen. So this is what we were seeing on the wall in the video before. That's the laser, and when I place the diffraction grating in place, I will be able to change the number of lines per millimeter, and then I will be able to change the wavelength, and then I can change the distance to the grating from the screen. Let's see what happens as the ray diagram, as well as what we actually see on the wall. Increasing number of lines per millimeter. This means I am dividing 1 millimeter into 500 lines. At the beginning, the millimeter was divided into 200 lines. So the width of each individual slit between each line is getting smaller. The pattern is getting wider and wider. This is exactly why, with a 600 per millimeter diffraction grating, we weren't able to see any interference maxima because the angle for the first maxima was too wide to fit into my view. As you can probably guess, larger wavelength would have further bright fringes, and vice versa. And as you move the screen closer, what we see is closer points because we are looking at a smaller distance. Now, what happens if we're not using monochromatic light? What if we are using white light? This is what my diffraction gratings look like. They're all labeled with number of lines per millimeter. This is my light source, and I'm going to be using these variations of diffraction gratings. When you look at a diffraction grating, it must be very hard to imagine what 80 lines per millimeter looks like. Well, it doesn't look like anything. It just looks like a blurred piece of glass. You can't really tell the lines, obviously, when they're that close. But when we put it in front of a light source, you'll see the effects. All right, let's put the 80 lines per millimeter in front of white light. Let's look with 100 lines per millimeter. See what happens here. With 300 lines per millimeter, we're seeing colors. With 600 lines per millimeter, did they just cut further? And with 1,000 lines per millimeter. Now let's see what happens on the screen. Screen with 300 lines per millimeter. Please observe that blue is always on the inner edge. Oh, we have two. And a third one on both sides. With 600 lines per millimeter. There we go. Again, blue on the inside, red on the outside. And the angle to these locations have gotten bigger. What do we see with 1,000 line per millimeter? Seems like we don't see anything until we look further away. There they are. So, why do we even use diffraction gratings? Why do we need diffraction gratings? If you studied in chemistry emission spectra of elements, you might have used this apparatus before. This is a spectrum tube which contains a certain gas, and when we look through a diffraction grating, we see its emission spectra. We will study what emission spectra is in a later unit in physics, but briefly, let me explain what it is. It's the lines that correspond to certain wavelengths that are emitted when electrons make transitions between energy levels in that particular atom of the particular gas. This information allows scientists to study the behavior of elements and even determine the composition of stars. So let's see examples of a few of these. A hydrogen with diffraction grating, without diffraction grating. Neon without diffraction grating. That's what it looks like with diffraction grating. Each of the lines on the sides you see are actually the minima of that wavelength. Well, air is a mixture of gases, so we see almost the full visible spectrum. Let's explain what they are. When white light goes through a diffraction grating, each of the individual points between the lines act as a single source, and a maximum forms just like the two-source interference pattern did at a certain angle depending on the wavelength of the light. If you're using monochromatic light, you would be seeing the maxima for those colors. If you use white light, you would see a maximum for red and a maximum for blue separately, which is why we see those colorful patterns when we see through white light, when we see white light through a diffraction grating, and always blue closer to the center than the red, because we know from what we learned before that a smaller wavelength would have a closer maxima to the center. And this is another image representing what we saw in the video before. If white light comes in, this diagram shows the red and the green. We would have green maxima here and the red maxima here. This is where all the colors have their maxima, so we see white as they are combined. Let's look at the ray diagram for diffraction grating. Let's start from the single slit that we discussed before. D, the distance to the screen, and that is my screen. So instead of a full single slit this time, we are going to be placing a diffraction grating in front of this single slit, which means this region is being split into tiny sources of equal size. So I'm going to represent them like this. So every section between them is a tiny source on its own. If this is white light, we're going to have a white constructive interference at the central max. If this was red light, I would likely have a maximum here, symmetrically one over there. If I was using green light, the first maximum could be there and there. In blue light, those would be the positions of the maxima. The central constructive is common for all, so that is why this region here would look white, because white is what we see when we have all those colors combined. The central max for all wavelengths. That would be the location of the first constructive interference for blue light. This one for green, and that one for red. As you can see, the first order of maximum would be at that angle for red and that angle for green and that angle for blue. But if I'm using white light, what I see is all of those colors together in the first order. So the first order maximum, second order maximum. Please realize that blue has always the smallest angle and red would have the largest angle. As you can see, the angle to the first maximum is measured exactly like we did in two-source interference explanation, always from the 0 degree to the first maximum. Now let's go with what we did for two-source interference. We defined path difference as n lambda for constructive interference. For the first order, n would be 1. Second order, n would be 2. We defined d as the separation of the two sources. Now, here, the d will be the distance between each consecutive slit. So if there are 80 lines per millimeter on my diffraction grating, the separation of consecutive slits would be 1/80 millimeters, because each millimeter is divided into 80 sections. So the width of each section would be 1/80 millimeters. We need to write everything in SI units, so let's write this in meters. S, distance between consecutive maxima. Do you remember how we derived this formula? We had to use the small angle approximation. Theta was equal to sine theta, because the angle was approximately 0. Angle was so small that we were able to make that approximation. Well, these angles aren't that small anymore, so we cannot approximate theta to be equal to sine theta. So in my formula, this was the angle. Now it actually has to stay as the sine of the angle. For first constructive interference, this was 1 lambda, and obviously 1s because we're measuring from the center to the first. But if we generalize this in n lambda for all orders of maximum, this becomes that. And rearranging gives d sine theta equals n lambda, where d is the separation of consecutive slits. As I explained above, that depends on how many lines per millimeter the diffraction grating has. Theta is the angle, and n is the order of maxima. So for the first one, after the center, n is 1. For the second one, n is 2. And obviously wavelength is lambda. You can even relate this to S over D, because like I showed in this simulation before, as the screen moves closer, the two maxima on the screen get closer. Like if the screen was closer, the S would be smaller and smaller and smaller, as you can see. So this summarizes the diffraction grating formula. You can use this to make your notes. A final word on comparing multiple slits and diffraction grating. If there are multiple slits, there are more sources added. If there's a diffraction grating, same source is split into more divisions. That means in multiple slits case, there's a constant slit separation. In the diffraction grating, as the number of lines per millimeter increases, the slit separation decreases. This means in the multiple slit case, same number of maxima observed at the same angles, the same locations. And in the diffraction grating, angle to each maxima increases because of the decreasing slit separation and slit width. In the multiple slits case, as you add more, the maxima get narrower and sharper. In the diffraction grating case, as we increase the number of lines per millimeters, the maxima spread apart. That's it for this lesson. Your homework is a virtual lab. This again is one of the prescribed labs for high levels in the physics syllabus. So that is the link. And here is the list of questions that you are supposed to answer. Thank you.